Alright, in this chapter, we're going to look at inverse functions, and you guys are going to find the inverse of a function by hand, and we're also going to graph a function and its inverse. Alright, when we talk about inverse relations, we're looking at two separate relations, one where the input and the output have been reversed. You'll have an original function, and then we will find its inverse. And if you look at a table of values, the inputs and the outputs will be reversed. So if you're looking at the first function, we've got 3x minus 5. This table is representing some x values. If you plugged in negative 2 through 2 into this function, these would be your outputs. G of x is its inverse. So if you switch x and y, if we were to plug in negative 11, negative 8, negative 5, negative 2, and 1, we would get out the same x values as the first one had. If you look at the two functions, notice the first function, we're subtracting 5 and multiplying by 3. In the second function, we're doing the exact opposite. We're adding 5 and dividing by 3. When we talk about a function and its inverse, we are also going to look at the domain and the range. Those are also switched. So if we look at the domain of this first function, f of x, that's just a line. It's in slope-intercept form. The domain of a line is all real numbers, and the range of a line is also all real numbers. If we look at the domain and range of this inverse function, this is really a line as well. You could rewrite that as 1/3 x plus 5/3. It's a little bit easier to tell it's a line because now you can see it's in slope-intercept form. So its domain and range are also all real numbers. Since we know they're inverses though, the domain becomes this one's range, and the range here becomes this one's domain. All right, so we need to know how to find the inverse of a function by hand or algebraically. To do this, what we're going to do is we're going to actually switch the values of x and y. So wherever you see an x in your function, you're going to switch it to a y. And wherever you see a y, you're going to switch it to x. We do this because, like we said on the previous page, the x and the y's are interchanged when you have a function and its inverse. To find that inverse function, you're then going to solve for y. So switch x and y and solve for y. This new function that you get will be your inverse, and we have some special notation that we have to use to represent the inverse of a function. We call it f inverse of x. So notice we put kind of like a -1 in the exponent position. And again, that's pronounced f inverse of x. So let's practice this. We're going to find the inverse by hand. And then we're going to also think about the domain and range of the original and of the inverse. So first of all, you see we have f of x equals 2x minus 1. We can rewrite that as y equals 2x minus 1, because remember f of x and y are interchangeable. This helps you see that then when you switch these, y is becoming your x and x is becoming your y. And all we need to do is solve for y. We're going to add 1 to the left and divide by 2. So x plus 1 divided by 2 is the inverse function of 2x minus 1. Notice we were subtracting 1 in the original, now we're adding 1. We were multiplying by 2, now we're dividing by 2. So the correct notation, since it was f of x to begin with, the inverse, f inverse of x, is x plus 1 divided by 2. So let's also think about its domain and range. This is the equation of a line in slope-intercept form, and we know the domain and the range of lines are always all real numbers. So if we switch the domain and range to get the inverse, they will still be all real numbers. Because again, this is still an equation of a line. You could rewrite that as 1/2 x plus 1/2 in slope-intercept form, and that's still an equation of a line. All right, so again on this one, we see that it's f of x equals, so we can rewrite that as y equals 2x to the 5th plus 3. We need to swap x and y because we're trying to find the inverse, and when you have the inverse, the x and the y are switched. And solve for y. So subtract 3 from both sides. I need to get rid of this 2, so divide by 2. And then to undo this exponent, we need to 5th root to that. So our f inverse of x is the 5th root of x minus 3 divided by 2. If we think about the domain and the range, we've got a polynomial function here with x to the 5th. There are no restrictions on this domain and range. You can raise any number to the 5th power without any restrictions, so we know the domain is all real numbers. And we are able to get out all real numbers as well. No matter what numbers I substitute in, I will always get out all real numbers. So again, the domain and the range of the inverse are both all real numbers. The domain is becoming this range, and the range is becoming this domain. They switch. We can, given two functions, verify that they're inverses of each other by using the composition that we learned last week. So if you do the composition of a function and its inverse, you should get out x. So let's say you have two functions, f of x and f inverse of x. If you do the composition f of f inverse of x, it should equal x. And likewise, if you do f inverse of x, that should also equal x. If you remember from the investigation we did today, when you graph a function and its inverse, they're reflected over the line y equals x, which is where this x is coming from. It's related to our graph of the function and its inverse. You must show both ways of the composition with f of x on the outside and on the inside. It must work both ways for you to be able to verify it. So let's try that with g of x and f of x. We're going to have to show f of g of x. We're going to have to show that that simplifies to be x. And we're also going to have to show g of f of x. You're going to have to show it both ways. If I do f of g of x, I've got f of 1/2 x minus 3/2. That means everywhere in x and f, I'm going to replace it with 1/2 x minus 3/2. So I have 2 times 1/2 x minus 3/2. I'm replacing x with g of x plus 3. So if we distribute the 2 times 1/2 is 1, minus 2 times negative 3/2 is negative 6/2, which is negative 3, plus 3. So that simplifies to be x. So we've confirmed that the composition works when we do f of g of x. We just have to show that it works for g of f of x. So now we're going to have g of 2x plus 3. That means everywhere in g that I see x, I'm replacing it with 2x plus 3. So I'm going to have 1/2 times 2x plus 3 minus 3. Again, distribute the 1/2. 1/2 times 2 is 1. 1/2 times 3 is 3/2. You subtract those, again, you get x. So you have confirmed that they are inverses of each other because both composition gave you the output of x. All right, so far we've just looked at mostly lines. So what happens if we look at inverses of nonlinear functions? So maybe of a quadratic or of a cubic. On the left, you've got the graph of the parent function of a quadratic, y equals x squared, and it's also shown its inverse, x equals y squared. Notice y and x have been switched. This dashed line, that's the line y equals x, and we know that a function and its inverse are reflected over that line. Over here is the graph of y equals x cubed. That's your parent function of the cubic. If you reflect that over this dashed line y equals x, that gives you the inverse of the cubic function, which would be x equals y cubed. If you compare both of the inverses, the inverse of the quadratic is not a function. We know this because it fails the horizontal line test. Remember, for something to be classified as a function, it has to have one output for every input. And if you do the horizontal line test, your horizontal line will touch your graph in more than one spot, multiple times. So we say that it fails the horizontal line test. Now, the inverse of the cubic function is a function. If you do the horizontal line test, every input has exactly one output. So what we can do if we know that a function's inverse is not going to be a function, we can do what we call restrict the domain. So we can restrict the domain of x squared to be either x is greater than or equal to 0, then you would only see the right side of the function because you would only have x values that were bigger than 0. Or you could restrict it so that x is less than or equal to 0. So then you would only see the left side of the graph. You would have x values that were less than or equal to 0. If you restrict the domain, then the function's inverse becomes a function. So let's look at one example where we graph a function that has a restricted domain. Again, normally the graph of x squared has a domain of all real numbers, but I want to restrict it so that its inverse is still a function. So if I wanted to graph y equals x squared with x values that are just less than or equal to 0, I could make a table of values to help me do that. I need to pick x values that are less than or equal to 0. So maybe I pick -3, -2, -1, and 0. Plug each one of those into your function. -3 squared is 9, -2 squared is 4, -1 squared is 1, and 0 squared is 0. So when I connect those, notice that I just have half of that parabola. Normally this graph would be reflected and be symmetric about the y-axis, but since I'm restricting the domain, I only see half of it. Now maybe I want to graph the inverse of this, so let's make a table that represents f inverse of x. All I have to do that is swap the x and the y values. So all my y values become my x values, and all the x values become my y values. So if you connect those, there's your inverse of that function. If I draw in the dashed line y equals x, notice the original has been reflected over that line to give me this inverse function. The inverse of this is still a function. If you do the horizontal line test, draw a horizontal line across your graph, every input has exactly one output, so we know that the inverse is still a function. We have a test that we can use to be able to tell if the original is going to have an inverse that is still a function, and we call that the horizontal line test. So we say that if the original function fails the horizontal line test, so that means that the line touches the graph in more than one place, then the inverse will not be a function. So here's two examples. This would be a polynomial function with a horizontal line going through it. If you can imagine this horizontal line scanning this graph, it's only ever going to touch it in one place. So that tells me that if I found the inverse of this, it would still be a function. Here's the graph of a quadratic with a horizontal line drawn across it. It's touching it in more than one place, so that means it fails the horizontal line test. So I can imagine if I had the inverse of that, it would not be a function. All right, so before you come in tomorrow, I want you to remember the rules for transformations of functions. What kind of transformations did we do with quadratic and absolute value? And how does each variable affect the graph? So I want you to remember what A, H, and K do to the graph of translated functions.